Hello my friends and welcome back to creating the architecture of the neural network. We are now at the second step of implementing this network class. We just implemented the init method to, build the different properties of the object, the future A3C eyes and brains that will be created later on. And now we're about to define the forward method to indeed forward propagate the signal from the input images up to the final two output layers of the action values and the state value. Alright, so let's do this. Let's start by defining the forward method, which will take as input self first for the object, and then of course, as always, the state. The state, which is of course input frames. Okay, so let's add some colon, and there we go. Let's forward propagate the signal. So we're gonna start from our state, right? That's the very beginning. Then we're gonna forward propagate the state to the first convolutional layer, and to do so we're going to call our self.conv1 convolution, which will take as input the state and which will return, of course, the signal in that first convolutional layer. Alright, so first step of the forward propagation done. Now we're just going to activate that signal thanks to the rectified linear unit activation function, also called rectifier activation function, also called relu. So here we go, you know how to do this. We first call our functional module, which has a shortcut f, from which we call, of course, the relu function, which takes as input, of course, x, right? That signal which we have to linearly activate. So now we're going to update x by just adding here at the beginning x equals. Okay, so now the signal is activated, and so let's continue the forward propagation. And so, well, let's do that efficiently. We're going to take that first line of code here. We're going to paste that here. And now, according to you, what do we need to change? Well, we need to change two things, of course. First, the convolution. We're now forward propagating the signal x from the first convolutional layer to the second convolutional layer, and therefore we use our second convolution conv2 to do such propagation. And of course here it's not going to take the state as input, but of course the signal x. Okay, perfect. So now the signal is propagated from the first convolutional layer to the second convolutional layer thanks to our second convolution. Alright, so now let's take this to activate once again this signal thanks to the rectified linear unit activation function. So let's paste that here. And here, of course, we have nothing to do because, again, it applies that activation function on our signal x here, which is then updated here. All right? So now let's smash that next step for propagating the signal from the second convolutional layer to the third convolutional layer thanks to the third convolution, and also while activating it. So what we're going to do now to make it efficient is take those two lines of code and then just paste them below. And of course here we're just going to replace self-conv2 by self-conv3, and voila, this is all we have to do to indeed forward propagate the signal x from the second convolutional layer to the third convolutional layer thanks to our self-conv3 third convolution object we created here. Okay, so perfect. Now the forward propagation is done through the different convolutional layers, and so now we're gonna continue that forward propagation from that last convolutional layer to the rest of the neural network. And speaking of the rest, well, what is the next step here in our neural network? Well, that's of course the flattening layer, right? We created that flattening operation here, which gives us the flattening layer, and therefore we're going to forward propagate now the signal from the third convolutional layer to that flattening layer. And according to how we're going to do that, well, that's super simple. We'll of course use our flatten object, just like our conv object and our fc object. So let's do this. We're going to call indeed our self.flatten object, which will take as input, of course, what? Our signal x. Okay, x here, which is currently in the third convolutional layer, and which we're going to forward propagate to the flattening layer. Alright, so that does the trick. And so now, well, we only have to forward propagate the signal from the flattening layer to the first and only intermediary fully connected layer, which is given by our FC1 linear full connection operation. So there we go, let's do that next step of the forward propagation. We call our self.fc1 linear full connection operation, which will take as input, of course, our signal x, and which will return that new signal x in the first fully connected layer. And then, of course, we're going to activate that. So we're going to add that same next line here, x equals f.relu of x. Perfect. So that activates the signal just forward propagated from the flattening layer to the first fully connected layer thanks to our first linear full connection. And so now, finally, what is the next and final step, or should I say final steps, because indeed now we have two final output layers, one returning the action values and one returning the state value. Well, that's exactly what we're going to do. We're going to get those final outputs in the two final output layers. All right, so let's do this. Let's start with the action values. Okay, which we're going to get by forward propagating the signal in the first fully connected layer to the final output layer thanks to our FC2A linear full connection operation. So, well, actually, let me take this here because that's exactly what we have to add next here, because indeed we're going to call our FC2A linear full connection operation, which will take as input, of course, our signal X. All right. And that gives us the action values, meaning the Q values for each of the different possible actions that the AI can play. Okay, just like what we did in the previous implementations of deep Q-learning and deep convolutional Q-learning. But now we're implementing the A3C, so we're also going to return the state value thanks to our other final full connection FC2S. And so I'm going to take my last object here, self.fc2s, I'm going to copy it, and here just below, I'm going to create that final variable of the state value. There is only one, right? And then I'm going to call, of course, our self.fc2s linear full connection operation, which will take as input what, of course? Well, still our signal X, right? Because we start from the same signal X in this intermediary fully connected layer, but then we call two final linear full connection operations to forward propagate the signal to different final output layers. One that will contain the action values and one other that will contain the state value. So there we go. That's exactly what we will get here. The state value in that final output layer returned by that second FC2S linear full connection operation. But here actually, in order to get the state value itself, we just want the value, not in any vector or any array. Well, we're just going to add here a pair of square brackets and then 0 inside to really access this value. Because, we will use this value in the future formulas of the A3C algorithm. Alright, and so now, according to you, what is the very final step that we have to do? Well, remember, the forward method is supposed to return those final outputs in the final output layer. And so that's exactly what we're going to do. We're going to return first the action values and then second the state value. Because, of course, we now have two final output layer, one containing the action values and one containing the state value. So congratulations, my friends. Well, actually, now it's time for me to say triple congratulations, because not only we are done with the forward method, but also we are done with the network class, and also we are done with part 1, building the AI. So let's not forget to run this cell to indeed have our model of the network class created, so that we can create anytime we want and as many as we want some brains of our future A3C models containing eyes and neurons, and that forward method as a tool to forward propagate the signal from the input images to the final two output layers containing the action values and the state value. And so now, well, let's get recharged in energy with a good coffee or tea or a good nap. And as soon as you're ready, well, join me in part 2, training the AI to train our brain we just created with the A3C intelligence integrated. Alright, so I can't wait to start this part 2 in the next tutorial, and until then, enjoy AI. Hello my friends, and welcome to part 2 on training the AI. We have now our network class, which gives us an artificial brain and some artificial eyes for our AI to be able to see and learn and understand some logic in the Kung Fu fight game. And so now it will be time to train it thanks to this part 2, and our first step here is to set up the environment. And so for this, as opposed to before, we have this preprocessed Atari class, because actually setting up the Kung Fu environment is a bit more complex, and therefore we need this preprocessed Atari class to preprocess it. But once again, since it doesn't have directly to do with building an AI, well, I chose to leave it here for us not to have to re-implement it, okay? But basically it has the init method, the constructor method, which defines the properties of the environment with the different object variables here, like the color, the observation space, of course, and the frames. Then you have the reset method to reset the environment, of course. Then the observation method to pre-process images of the environment. And then you have the update buffer method to update the buffer. The makeOnv function, so be careful, this is outside of the preprocessed Atari class in order to, well, actually create the environment variable while using the preprocessed Atari class to, well, preprocess it. And then we have the environment here. Okay, here this is really where we get for real the Kung Fu environment. And then for the rest, well, you know this very well. We implemented that in our deep Q-learning and deep convolutional Q-learning implementation. We first get here the state shape, then the number of actions, and then we do those sprints. But here I just added this extra sprint, which will give us the action meanings, exactly like what we saw, remember, in the description of the actions here. We will get all these in our console once we execute the code cell. So, speaking of which, let's do this now. Let's run the cell and let's see the state shape, the action size, meaning the number of actions, and of course the action name. So here's the state shape. Remember that the state is actually a stack of 4 grayscale images, so these correspond to the 4 here, and then of which dimensions? Well, 42 by 42. Therefore, the states are going to be stacks of 4 images of dimensions 42 by 42. Right? Pretty clear? And then we have our 14 actions. So we have 14 possible actions that the AI can play. And they are right here. Noob, up, right, left, down, right, down, left, left fire. Exactly like what we saw here. Okay? Perfect. So now it's very clear what the input states is, what the actions are. And so, well, we can move on to the next step, which is, just like before, to initialize the hyperparameters. So let's create a new code cell. And here we actually have 3 hyperparameters to initialize, which are similar to the ones we saw before, except one, which is totally proper to the A3C model. So let's start with the ones we know. First, we have, of course, the learning rate, which we will initialize to 10 at the power of minus 4. All right, I think it's the same value as the one we used before. And of course, it's going to be the learning rate of the Adam optimizer we will use to, update the model's parameters, meaning the weights of the neural network when we backpropagate the loss into the neural network. So that's for the learning rate. Then another hyperparameter, which you know very well, which we used already twice in the deep Q-learning and deep convolutional Q-learning model, is of course the discount factor. So here the discount factor is the hyperparameter that will be used in the formula that will compute the target state value. We will see that when we implement the A3C class. And so, just like before, we're gonna initialize this discount factor to 0.99. Alright? It looks very familiar so far, right? But now, here is where things change, because now we're about to initialize a hyperparameter which we haven't created anytime before. I mean in this course. And I'm talking about a very exciting hyperparameter because it's actually the number of, can you guess what it's going to be? Not the number of actions indeed, but the number of environments. Right? This is totally proper and specific to the A3C model because in the A3C model, we actually train multiple agents in multiple environments in parallel. And that's the super brilliant part of this algorithm. Indeed, each of these multiple environments will be typically run in their own process and inside which an independent agent will interact in each of these environments. So that's the really cool thing I think about this A3C algorithm. And there we go. We are about to initialize this number of environments variable. And how many environments will we choose to, train those multiple agents in parallel? Well, we're going to choose 10 environments, and that should be enough. And by the way, this particular feature of the A3C algorithm is one that considerably improved the training performance. Thanks to this idea of training multiple agents in multiple environments at the same time in parallel, well, will significantly speed up the learning process and help the overall algorithm to converge much faster. And you will see that in the final result. You will see that we reach convergence of the score very, very fast. I can't wait to show you this. So there we go. That's all we need to initialize here. So we're gonna run this cell and perfect. Now please get some good energy because indeed the next step is to implement the A3C class, which will be of course in that new agent class as we did before, only this time it will contain the A3C algorithm. I can't wait to implement this. Please recharge in great energy, get some good coffee or tea or a good nap, and as soon as you're ready, join me in this next tutorial to smash this A3C agent class. And until then, enjoy AI. Hello my friends and welcome to this next step of the training implementation where we're going to implement the A3C class. So it will be a very exciting step. It's of course the step where we implement the agent class just like how we did with our deep Q-learning model and deep convolutional Q-learning model. And once again, just like before, it will be a class that contains, well, the init method for sure to define the object variables, then the act method in order for our AI to play an action. And this time it won't be an epsilon degree policy, just like we did before, but a softmax max policy. Alright, so it's good that you know several strategies. And finally, so this is pretty interesting because both in the deep Q-learning or the deep convolutional Q-learning implementation, remember when we implemented the agent class, well, we had a learn method at the end, right? Which is called, in fact, into the step method. But this time for the A3C model, we won't implement separately a learn method. We will directly integrate that into the step method so that we only have to implement the step method. Therefore, the agent class that we will build now for our A3C model will only contain 3 methods: the init method, the act method, and the step method. Alright? And of course, we're going to start now with the init method. So let's create a new code cell. And here we go. Let's start by declaring our class. So of course, we're going to call it agent, just like before. Then nothing to input in the parentheses. We can add some colon. And there we go with the init method. So we start by defining it with def, then double underscore, then init, then double underscore again, and then, according to you now, what will it take as input? Well, first, of course, self for the object, but then what is the other argument? Well, it's exactly the same as the deep convolutional Q-learning model. Our A3C model has artificial eyes, which allows it to see some frames, some input images, which are the states. Remember, these are stacks of 4 grayscale frames of dimension 42 by 42, and therefore there is no such thing as a state size, just like in the deep Q-learning model. And so we're going to do exactly the same as in the deep convolutional Q-learning model. We're just going to input here an action size argument, which is of course the number of actions. Alright, so let's do this. Let's just enter action size, and there we go. We're ready to implement our init method. Alright, so now we basically have to define the different object variables, and we're actually going to start with self.device, which will be the CPU or GPU to which we send the computations. And so, well, just like before, we're going to call our torch library, from which we're going to call the device function, inside which we're going to enter first in quotes CUDA colon 0, and then outside the quotes if torch dot CUDA dot, and then remember this function is underscore available. There we go, perfect. Then some parentheses, and so that means that indeed if CUDA is available, then we will use it. We will use the GPU, or if it's not available, then we're going to add here else, and we're going to enter in quotes CPU. We're going to use the CPU, okay? Just like we did before with our deep Q-learning and deep convolutional Q-learning implementation. So all good here. Now, next object variable. All right, so the next variable is going to be super simple. It's going to be the action underscore size. And how will we initialize it? Well, of course, to the argument that will be input here when we call the agent class to create an instance of that class, which will be our A3C agent itself. Okay, so let's copy this. Let's paste that here, and there we go. Now we have our action size object variable. Now, next object variable. Well, according to you, what does our agent always need in order to be trained? Well, that's of course the brain, right? The brain that we can get from our network class, which we implemented in part 1. And so that's exactly what we're going to get now. But remember, in the previous implementations in deep Q-learning and deep convolutional Q-learning, I can show you any of them. The way we created the brain is actually through the creation of 2 brains, the local Q network and the target Q network. And it was the same in deep Q-learning. But now we're implementing A3C. Therefore, there is no question of local or target Q network. There is only one network. Well, when we create one agent, and therefore we're simply going to call that self.network. Okay? Or you can even call it self.brain if you want. Okay, so self.network, and then, well, how do we create it? By, of course, calling our network class, which takes as input what, of course? Well, only the action size, just like in our deep convolutional Q-learning model. So action size, and this is, of course, the argument here. So all good, we can just keep that. And then finally, we're going to send this to the proper device, CPU or GPU, which is given by our self.device object variable we created here. Okay, self.device, perfect. Now we have our brain. Great. And now, what is the final thing we absolutely need in order to train our A3C agent? Well, we have the brain, that's good, it's ready to be trained, but which tool do we need exactly to train this brain? It is the tool that will, update the models parameters, meaning the weights of the brain, inside the neural network when back propagating the loss back into the neural network. Well, I'm talking, of course, about the optimizer. And there we go, that's our last object variable here, self.optimizer. And how will we create it? Well, we will create it as an instance of the atom class, which we get from the optim module by the torch library. So here we go, we call the torch library first, from which we call that optim module, from which we call that atom class. Alright, and remember what this atom class takes as input? Well, it takes first the parameters of the neural network of our AI, which is of course self.network, then dot parameters to return those parameters. So that's exactly what you see here with the first argument. So here we go. Let's enter that. So we call first our self.network, which we just created right here in the previous step, self.network. Perfect. Then dot, and then we call this parameters method, a method of the network class, which indeed returns those models parameters, meaning the weights of the neural network we created in part 1. Okay, so that's for the first argument. And now what is the second one? Of course, whenever you use an optimizer, you always consider the learning rate, right? Just like what we did before with deep Q-learning or deep convolutional Q-learning model. Indeed, the learning rate is one of the essential parameters of the optimizer. So here we go, let's input it here, LR equals, and well, it's going to be equal, of course, to our learning rate that we have here. So we can copy it if you want and paste it right here. All right, and that's it. That's all we need to define for our agent class, in terms of object variables. So now that means we are ready to move on to the next step, which will be to implement the act method, which will allow our agent to play an action according to, this time, a softmax strategy. So it will be a very exciting step, the first time we implement softmax in this course. I look forward to seeing you in that next tutorial, and until then, enjoy AI.